Okay, so here's some examples of how we can use ratio and, in fact, proportions to solve for unknown situations in a geometry problem. So for example 1, we have a triangle. The measures of 3 angles in a triangle are in the ratio 2 to 2 to 5. So we don't know what the angle measures are, but we do know that whatever they are, they have a ratio of 2 to 2 to 5. And using this information alone, we can actually find the measure of each angle. Now, this might seem a little bit surprising that we can find these with so little information. But what you have to remember about ratios and proportions is the ratio of 2 to 2. If I have a fraction like this, or any ratio, like if my ratio were 1 to 2, I can convert it to an equivalent fraction by multiplying by anything over itself. So, 1 over 2 times 3 over 3 is still equivalent to 1 over 2. I get 3 over 6. And this isn't just numbers that we know. I can also use variables to do this. So 1 over 2 times x over x gives me x to 2x. And that's still the same ratio as 1 over 2. There's no difference here, because the x over x, if I simplify this, it will cancel and I'll get 1 over 2. So the trick to a problem like this is to consider the ratio and then consider multiplying all parts of the ratio by the variable that you're looking for, at least in the cases where that's appropriate, like here it is, because we know that whatever this angle is, 2 times it, x, will be the same as 2 times this angle. And this relationship of 2 to 5 means that this angle is going to be 5 times, not 5 times this angle, but 5 times x. 5 times, or it'll be a relation of 5x to 2x. So I can actually represent all these angles using that variable. Okay, it doesn't have to be x. You can use whatever you like. But what do we know about all of the angles in a triangle? Well, they sum to 180 degrees. So using this ratio, I can establish the following equation. I can say that 2 times that first angle plus 2 times the second angle plus 5 times the third angle. If I add all of those angle measures together, I get 180 degrees. And so this becomes 9x is 180. And so x will be 20. X is 20, which means that the measure of each angle, okay, that doesn't mean this is 20. That means it's 2 times 20. So this angle is 40 degrees. So let's just call these angles A, B, and C. The first angle is 40 degrees. The second angle is the same, 2 times 20. And the third angle is 5 times 20. And we've discovered the measures for all of the angles in the triangle using ratios. And in fact, don't tell anyone, we're skipping ahead, we're cheating a little bit here, but you can't do this without a proportion. Any equal statement really in reality is a proportion, because I can always represent numbers as fractions. I can think of this whole side as 9x over 1, and this whole side is 180 over 1. And so I have everything I need that matches the definition of a proportion. I have a ratio on one side being said equal or stated to be equal to some ratio on the other side. So even though these problems that we're going to work are taken from the section on ratios only, you can't actually solve any of them without using proportions, which are covered more in the second section of the chapter. So understand that. Like, ratios are not usually all that useful if you don't have proportions to work with, if you don't have some kind of equality statement that you can use. Second example, the ratio of the measures of 2 supplementary angles is 11 to 4. Find the measure of each angle. Okay, that means that 11 times whatever the first angle is corresponds to 4 times whatever that same value is. So this larger angle of the two is going to have a proportionality value of 11 compared to 4 for this one. So just like with the triangle, that means this angle is basically, we can represent it as 11 times some variable, and this angle as 4 times some variable. What do we know about supplementary angles? They add to 180 degrees. So 11x plus 4x is equal to 180, which gives me 15x. And when I divide by 15, let's see what this is going to be. So we get 12, so x is equal to 12. 11 times 12 is 132. 4 times 12 is 48. And you'll see if you add these together that they will equal 180 degrees. So that's a good way to check that we've done things correctly here. So the two angles are 132 degrees and 48 degrees in this case. All right, one more example. Now, this one's a little more complicated and calls on a little bit more outside knowledge, but we will explain. A baseball player has a batting average of 320. Okay, your batting average is the percentage of the number of times that you get a hit when you go up to bat versus compared to your total number of at-bats. So percent is always out of some total number. So the 320 is a decimal. As a fraction, what it represents is 320. We have 3 decimal places here, which means we're talking about thousandths. This is the same thing as the fraction or the ratio 320 over 1,000, or 320 to 1,000. This baseball player has been at bat 325 times total. Okay, so a batting average of 320 means out of 1,000 attempts, 1,000 at-bats, he would get 320 hits. Okay, that's what the number represents. That's what the percentage, the decimal, represents in this case. This particular player has gotten this percentage by only going to at-bat 325 times, though. So he got this number out of 325, not out of 1,000. So the question is, how many hits did he get? Okay, this is 320 is the hits to at-bats. Well, we have a comparison between hits and at-bats here. We have a comparison between hits and at-bats here. And this number, 320, this is coming from this division, in fact. This is the result of this division. When I divide this, I will get his batting average. So you can actually, what we're doing here is we're establishing a proportion between these two. This ratio of hits to at-bats is the same as this ratio of hits to at-bats, or this percentage. So you could write the proportion like this, or in fact, since a decimal is in fact convertible to a fraction, you could just write it like this as well. You just say x over 325 is equal to 0.320. Since we're learning proportions though, let's keep it to the fractional form for the moment. So all I have to do here is solve for x. Okay, and again, this is where we're going to need to cross multiply. You can do this the longer way if you like, but it's a couple more steps. So we're going to cross multiply to solve this. When I cross multiply, I rewrite the equation by multiplying the numerator on one side of the proportion by the denominator on the other, and the denominator on that side by the numerator of the other, and then setting those equal to each other, those products. So 1,000 times x is equal to 325 times 320. Now, if you don't believe that this works, wait for tomorrow's lesson. We're going to talk about these properties of proportions and why we can actually get away with doing this, okay, taking this cross multiplication shortcut. It does work. And so x is going to be whatever this is divided by 1,000. So the number of hits that our baseball player gets when we perform this calculation, just double check this, is actually 104. So out of 325 at-bats, he got a hit and got on base due to his hit 104 times, which might not seem like a lot, but actually that's an excellent batting average. That's very good for, at least for professional baseball. Okay, now a little extension or a wrinkle on the question here. If he goes into a slump, so if you're not familiar with what a slump is when you perform poorly for a continuous length of time, for some extended period. It's not just like you strike out once or twice, or you fail once or twice. You fail consistently for a period of time. So he goes into a slump, he strikes out the next 10 at-bats. So the next 10 times he goes up to the plate and tries to get a hit, he's not successful. He strikes out. He fails miserably. What will his batting average be then? Okay, well, what are we changing here? We're changing the total number of at-bats that he's getting. Okay, he's going up to the plate 10 more times. So his number of at-bats is going to increase by 10. But he's not increasing his hits at all. His hits don't go up. So we know his hits are still going to be 104. So the ratio is 104. And his at-bats went up. We're comparing that to his at-bats. So he had 325. He went to bat 10 more times. So we add 10 to 325. And then that will give us some new batting average. It will give us some new number of, or a new success rate, a new number of hits out of 1,000. And so this is now the proportion that we want. Okay, and if I can do this, or if you understand how decimals work, we can just do the division here, 104 out of 335, and that will give us a batting average of 310, and a little bit more, but we're going to go ahead and we're going to round it to thousandths place. So his batting average will drop 10 points, or it will drop actually a tenth of a percent, or excuse me, it will drop 1%. It will drop 1% if he goes for 10 consecutive at-bats after this point and doesn't get a hit in any of those. Okay, if we solve this with the fractions the long way, again, you can cross multiply here. So 335 times x is 104 times 1,000, so 104,000. And when we divide by 335, we're going to get this same, that will give us the number of hits. It won't give us this decimal. It will give us 310 hits out of 1,000, which 310 out of 1,000 is going to be this fraction, or this decimal here. Okay, if you're confused by any of this, as always, give me a call or send me an email or post comments on the YouTube video, and we will help you out as best we can. All right, good luck. You've seen the assignment on the new high school daily syllabus, I guess you could call it. So you already know what you're expected to do with this. Turn that in tomorrow, please, and God bless, and have a good rest of your day.